Hello, welcome. I am Aubrey, and I am working on math. Okay, okay. So sorry. We are working out kinks, as always, aren't we? Okay, so today I had the good fortune of learning integration by parts. In all right. Okay, I thought I could do the music. I can't do the music. Um, Good news for my CPU. Um, okay, and we're back. Oh wait, let me open up my. Oh, there's a viewer. Hi, viewer. Let me. There's my chat. Cool. What's up? So that's what we're doing. It is a method for determining an antiderivative. So this is our integration by parts formula. Now he covered how to derive this formula, but you see, my iPad is in dark mode, and when I convert it to PDF, it's in light mode and it's saved in light mode, and I wrote in the color yellow and I can't at all see it, so I can't tell you how it's derived. I can tell you that there's apparently two different ways to do this, whether you're in the United States of America or whether you are in Europe or some other countries. Um, Anyways, it's kind of cool. I really don't want to go into what all of this is, but I suppose I should because I'm trying to, remind myself and put it better into my head. So he talked about how there were two different classes. Well, actually, there's like five classes, but we went over two of them. Um, the first one is when our problem is in the form of a to the x times t to the x dx. Um, so finding the derivative of two different functions, which is what this is. Like, say it's like 2x to the third, and then this one is sine of the 3x. So to find the antiderivative of this is not the simplest, and it requires using this method. So we'll just that wasn't a real problem, but that was just like basically the issue, because an antiderivative is, say if our function was 3x squared dx, we would add 1 there and then divide by the new number, and then our antiderivative would be x cubed plus a constant. So oh, okay, there we go. All right. Thank you so much for bearing with me. I'm sure this isn't the most interesting thing to watch. However, I think math is pretty cool, and I think passing math is even cooler. So basically, the reason that this says a of x and this says t of x is because it's talking about the different kinds of functions. Um, there is polynomial functions, which are plus, minus, and times. There are functions that involve those operations. There are rational functions, which are all of those, but they also add division into the mix. Um, I'm trying to think what's after that. I don't really remember. Let's see here. Well, anyways, there's something that adds in, the next one adds in plus, minus, times, division, exponents. Maybe it's not exponents. It's roots. And maybe rational exponents. That sounds right to me. So that means like 2x to the 1 over x, that would be a rational exponent because it's division. Anyway, somewhere in the mix of all this crap, one of the different kinds of function are called transcendental functions, and they include like ln and log and sine and cosine and like inverse trig. So that's what this is saying. So it's algebra. Oh, that was the word that was the one, the next one, algebraic. That was the one that includes roots. and irrational exponents. Algebraic, and then transcendental, it's in the center somewhere. But anyways, so yeah, that's basically just saying like a function kind of like this times, so I don't know if this function is solvable, so I'm not even gonna fuck with this one. I'm just gonna go to one from my notes that I know for sure. Okay, first example. All right, so our first class states that we're going to find our variables a certain way in the event that one of these derivatives becomes easier. So, becomes easier than the original problem. So in this function, or in this integral, our functions are x and ln of x. So the derivative of ln of x is going to be 1 over x, which by math logic, by logic, I guess, 1 over x is easier to work with than ln because 1 over x I think would be considered algebraic, and or maybe even only rational. One of the two, algebraic or rational. And this is a transcendental, so it becomes easier. So since this is the case, u is going to become the ln of x. Now with the integration by parts formula, you can see we have a u variable, and we also have a v variable. So this little thing right here means we're taking the derivative of v and the derivative of u. So the key to doing this problem is figuring out u and v. Well, okay. You find out u and you find out the derivative of v, which in our problem is going to be x. Okay, so I guess, yeah, so the other function, so the way I learned it was the rest of it is like dv would be x dx. But according to my teacher, that is the European method mixed with the American method or something, and that's wrong. And oh my God, it has been so fun learning calculus all over again with a brand new teacher with his totally different methodologies and thought processes. Anyways, he's great though. Anyways, so dv is going to be x because it is the other function in our problem. So now we want to find the derivative of u with respect to x. the derivative of u, as I said earlier, is going to be 1 over x, and that is because the derivative of ln over any expression is going to equal that expression's derivative over the expression. So in our case, since u is ln of x, x becomes our u. The derivative of x would just become a constant number, 1. And on the bottom, we would just write x. And so that's how we get 1 over x. Okay, now, so since we have the derivative of v already, we need to work backwards now and find the antiderivative. Kind of like what we're doing up here, but for like a smaller part of the problem. So the antiderivative of x, the way you find that out is so our exponent right now is 1 technically, it's x to the 1. So we're going to add 1 to that, and it will become x squared. But now we also have to divide by 2. Okay, so let me write that in the right spot. So x squared divided by 2, or you could write it as 1/2 x squared. Doesn't really matter. What really matters is now we have this information we want for this formula. So let's go ahead and just plug it in. We've got the ln of x times the derivative of v, which is going to be x. And we're going to write the x before the ln of x, but I mean, it doesn't really matter. You could write an ln of x. It just is kind of hard to interpret, I suppose, that way. You could write it with like parentheses. Anyways, it's just common to write the x first. So we've got u times the derivative of v dx. And that's going to be our original problem. So now we're going to have u times v. Minus the antiderivative of the derivative of u times v dv. So So you think that would be times x? I don't think so. Okay, so we got to simplify this. So we're going to have x squared over 2x. So the x is going to cancel there. The exponent's going to cancel there. And we're going to be left with x over 2. Oh, okay, so I did something wrong. Let me go back here. So I thought I was going to simplify, gosh dang it. I thought I was going to simplify this before I took the integral of it, but that's not exactly how they want me to do it. They want me to bring my constants outside of the integral. So that's going to be a 1/2 that comes to the outside of the integral. And then we are left with x squared over x, which would be just be x, right? Yes. Dx. Okay, so now we take the antiderivative of x, and we are left with this, and then we add our constant number. We're not done yet. I guess we don't have, we can't, we can wait to add our constant number for just another second. Let's see here. X squared x over 2 minus and I was correct. I was correct. All right. So it's kind of a lengthy process, I suppose. But you do what you have to do. Excuse me for just a quick moment. I'm going to go grab myself a little snack. Don't go anywhere. All right, moving onward. My teacher is really good, and I say this because it is not easy to try to teach this stuff. Maybe it's because I don't know it that great, but it's not. I mean, anyways. So you would think that this problem does not require our integration by parts rule, but well, you might not think that, but if you kind of know, like, so the whole reason we're doing integration by parts is because it's when it's like two different functions times each other. But this really just seems like it's one function. It's just the ln of x. And it's for that reason it's really confusing because you would normally think it would be like 3x times the ln of x, and that's why you would need to do it because it's two functions, blah 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 blah. But in this example, you do still need to use integration by parts because we don't have an antiderivative for the ln of u, which I haven't. Um, ay, ay, ay. Bless me. Um, let's see. My teacher said there is no antiderivative. And by golly, he's right. So we are back. So, anyways, the reason ends up being because there are two functions, and it is ln of x and 1 of dx, or 1 dx. So, according to our class number 1, we're first going to check and see if finding the derivative of either of these functions makes the functions themselves easier, which usually it's kind of obvious when it's an ln that it's going to make it easier because that ln is like we did in the last example. It's going to turn into 1 over x. So this indeed does become easier. So our u is going to be the ln of x, and then our dv is going to be 1. Derivative of u, 1 over x. The antiderivative of 1 It's x. Okay. Now we need our formula again. So here is our formula for integration by parts. Okay, let's plug it in. Ln of x times 1 Okay, so this is indeed what we started with. And now we do the ln of x times x minus the derivative of 1 over x times x dx. Okay. Okay, so this cancels, simplifies to the antiderivative of 1 dx. 1 dx becomes x, and then we add our constant. Oh, excuse me. Oh my god, my battery is dying rapidly. Alright, we're going to try to do one more problem. Gosh, I just can't hardly see it. Alright. Okay. This is an example, kind of one of the problems I made earlier, where it's like an algebraic function times a transcendental function. Which, what do you know? That's what it is. But It may not be this class because we have something to determine to figure it out. So, say we were to make u the sine of x. Now we want to find the derivative of u, which is going to be cosine of x. Um, this is transcendental. This is also transcendental. It is not easier. So let's try x squared. I'm going to argue that this is still, I mean, I don't think it's an argument. I think it's a pretty wrapped up case. That isn't easier either. So that means this is going to fall under our second class. And our second class states that if the antiderivative of v or is it okay, so our u is going to be x squared and our du is going to be 2x. However, it's not easier still. So then our second class states that we should use integration by parts if this integral is no more difficult. So our first case is if the derivative is easier than u. And our second case is if the integral of dv is no more difficult. Okay, so that's how we get there. Now, back to our formula, which is going to be u times v minus the antiderivative of v dx, I believe. v. Okay. Okay, so I did this wrong. I don't understand. Okay. Oh, u prime v. All right, well, forgive me. All right. Back it up. Back it up. You got it. Okay. So we're doing the integral of the derivative of u times v. v. So we're going to have to do integration by parts twice. So hooray! I got it. That was hard. So I forgot to mention that um, this value usually is a forecast for the number of sets of integration by parts you are going to have to do. Oh my gosh, my Macintosh is dead, literally. Oh my God, 9%. I gotta go. Much love. Thank you so much to Angie for watching my music streams always and being so nice. And oh, oh, sorry. Thanks to everybody for what. Thanks to whoever was just watching my stream now. I don't know who it was, but thank you so much. Good night. Bye bye.